Now we are going through invertible matrix. Let us see what is an invertible matrix. If A is a square matrix of order m, and if there exists another square matrix B of same order m such that A into B is equal to B into A is equal to I, then B is called inverse of A, and it is denoted by A inverse, A raised to minus 1. That is not A raised to minus 1, okay? A inverse of the matrix A. And in that case, A is said to be invertible matrix. It is the definition. If A is a square matrix of order m, and if there exists another square matrix B of same order m, such that, see, it is the condition, okay? AB is equal to BA is equal to I, okay? A into B, multiplication of A and B is equal to B into A. That should be equal to an identity matrix. Then this B is called, okay? Then we can say B is the inverse of A, and it is denoted by A inverse, okay? And in this case, A is said to be invertible matrix. Look at an example. Here two matrices are given, A and B. Now let's check whether if A is invertible or not, okay? Invertible matrix or not. So for that, we have to find, it is the condition, okay? AB, so it should be AB is equal to BA is equal to I. So we have to find AB and BA. A into B, that is equal to, okay, let us multiply from here itself. First row multiply with the first column, 2 into 2, 4, plus 3 into minus 1, minus 3. Okay, so first row multiply with the second column, 2 into minus 3, minus 6, 3 into 2, plus 6. Here, second row multiply with the first column, 1 into 2, 2, minus 2, okay, 2 into minus 1, minus 2. Second row multiply with the second column, 1 into minus 3, minus 3, 2 into 2, plus 4. That is equal to 4 minus 3, 1, 0, 0, 1. Okay, we have got AB is equal to I. It's an identity matrix of order 2, right? Okay, next we will find BA. Okay, it should be I. BA, that is B is this one, 2 minus 3 minus 1, 2 into 2, 3, 1, 2. Multiply these two matrices. First row multiply with the first column, 2 into 2, 4, minus 3 into 1, minus 3. Okay, first row multiply with the second column, 2 into 3, 6, minus 3 into 2, plus 6. Sorry, minus 6, right? Minus 6. My second row multiply with the first column, minus 1 into 2, minus 2, 2 into 1, plus 2. Second row multiply with the second column, minus 1 into 3, minus 3, plus 4. It's also 4 minus 3, 1, 6 minus 6, 0, minus 2 plus 2, 0, minus 3 plus 4, 1. So it's also an identity matrix of order 2. So here we have got AB is equal to BA is equal to an identity matrix I. Okay, so here we can say A is an invertible matrix or B is an invertible matrix, and B is the inverse of A is the inverse of B. Okay, now we will go through a theorem. Two more theorems we will study in this chapter. So next, third theorem. The theorem is uniqueness of inverse, very important. So inverse of a square matrix, if it exists, is unique. That means, see, suppose A is a square matrix, okay, and it has only one inverse matrix, okay. So here we have to prove this. That is, for any square matrix, if it exists, there is only one inverse matrix, okay, that we have to show. So for that, let us take, let A is equal to Aij be a square matrix, okay. Here we have to show there is only inverse matrix. For any matrix, any square matrix, there is only one inverse matrix, okay. That is the uniqueness, okay, uniqueness of inverse. So here we have taken a matrix A be a square matrix. Then, if possible, let B and C are B and C be inverse matrices of A. Okay, here we have taken two inverse matrices. Okay, here we have to show there is only one inverse matrix. For that, we have taken two inverses. Okay, now what we have to show? We have to show B is equal to C. Okay, for uniqueness, we have to show B is equal to C. So here we have taken B and C be inverse matrices of A. Okay, then by the definition of invertible matrix, we can say since B is an inverse matrix of A, by the definition of invertible matrix, we can write A into B is equal to B into A is equal to I, isn't it? Okay, and since C is an inverse matrix of A, C is also, we have taken B and C are the inverse matrices of A, right? So, since B is an inverse matrix of A, by the definition of invertible matrix, AB is equal to BA is equal to I, right? Similarly, since C is an inverse matrix of A, by the definition of invertible matrix, we can write CA is equal to AC is equal to I, right? Okay, then next here we have to show B is equal to C, right? For the uniqueness means we have to show there is only one inverse matrix. Okay, so for that let us take, we can write this B as B into I. What is an I? An identity matrix, okay? So any square matrix multiply with an identity matrix, we will get that matrix itself, right? So here B is equal to Bi. B can be written as B into I. I is an identity matrix. Okay. That is equal to B into, see, we will write B into AC. Okay. That is equal to, see, I can be written as AC because we know that AC is equal to I. Now, here by the properties of multiplication of matrices, we can write B into AC is equal to BA into C. Okay, by the properties of multiplication of matrices. That is equal to, see, what is BA? BA is nothing but I. Okay, so I into C. So what is I? I is an identity matrix, right? So I into any matrix, that is equal to that matrix itself. That is I into C is equal to C itself. So here we have got B is equal to C. That means there is only one inverse matrix. For any square matrix, if it exists, okay, inverse of a square matrix, if it exists, is unique. That is, here we can write, hence, inverse of a square matrix is unique. Okay. Next theorem is, If A and B are invertible matrices of the same order, then AB whole inverse is equal to B inverse into A inverse. So here, given that A and B are invertible matrices, okay, by the definition of invertible matrices, we know AB is equal to BA is equal to I, right? Or we can write A is equal to B inverse, B is equal to A inverse, right? That is, A is the inverse matrix of B and B is the inverse matrix of A. And here let us substitute here. See, we can write A into A inverse is equal to I, right? Or B into B inverse is equal to I. Okay. So in this form also we can write. Okay. So here AB is equal to I, right? So A into B is equal to I, an identity matrix. Okay. So an identity matrix, its inverse is an identity matrix itself. Okay. Inverse of an identity matrix is an identity matrix itself. So we can write here AB into AB inverse. Okay. An identity matrix, and its inverse is also an identity matrix, that is equal to I by the definition of the inverse of a matrix. See here. Here we have written A into A inverse is equal to I. A into inverse of A, that is equal to I. Okay. So here AB is an identity matrix, right? Because by the definition, because it is A and B are invertible matrices. So AB is equal to I. So AB is equal to I and its inverse matrix is AB inverse. Okay. It's also an identity matrix, that is equal to I. Then, now let us multiply A inverse on both sides. A inverse into AB inverse is equal to A inverse into I. Okay. Then, by the properties of multiplication of matrices, this can be written as A inverse into A into B, AB inverse is equal to A inverse I. Okay. Then, A inverse I means A inverse itself, right? Okay. So here A inverse A, that is nothing but I, right? A inverse A or A inverse or A inverse A, because A is an invertible matrix. So we can write A into A inverse or A inverse into A, that is equal to I. So A inverse A is I into B into AB inverse is equal to A inverse. Okay. I into B, an identity matrix into B, that is B itself, right? So B into AB inverse, AB whole inverse is equal to A inverse. Okay. Then now let us multiply B inverse on both sides. That is B inverse into B, AB whole inverse is equal to B inverse into A inverse. Okay. Here we have multiplied B inverse on both sides. So here B inverse B is nothing but I. Okay. So I into AB inverse is equal to B inverse A inverse. So I into any matrix, that is equal to that matrix itself. So AB into AB inverse is equal to B inverse A inverse. That's all. Look at an example. If A is equal to square matrix minus 3, 1, 5, 0 and B is equal to square matrix 0, 1 by 5, 1, 3 by 5, then show that A is invertible matrix and B is its inverse. So here we have to show, to prove A is invertible matrix and B is its inverse, we have to show AB is equal to BA is equal to I from the definition of the matrix, invertible matrix. Okay, so let us find A into B. Minus 3, 1, 5, 0. B is 0, 1 by 5, 1, 3 by 5. That is equal to, first of all, first row multiply with the first column. Minus 3 into 0, 0 plus 1. First row multiply with the second column. Minus 3 by 5 plus 3 by 5. Next, first row multiply with the first column. 5 into 0, 0 plus 1. sorry 0, right? 5 into 0 plus 0 into 1, that is 0. Second row multiply with the second column, 5 into 1 by 5, 1 plus 0, that is equal to 1, 0, 0, 1. It is an identity matrix of order 2. Next we will find B into A. 0, 1 by 5, 1, 3 by 5 into minus 3, 1, 5, 0. That is equal to, first row multiply with the first column, 0 into minus 3, 0 plus 1 by 5 into 5, 1. First row multiply with the second column, 0 into 1, 0 plus 0. Second row multiply with the first column, minus 3 plus 3 by 5 into 5, 5 cancelled, so plus 3. Second row multiply with the second column, 1 into 1, 1 plus 3 by 5 into 0, 0. That is equal to 1, 0, 0, 1. It's also an identity matrix of order 2. So we have got AB is equal to BA is equal to I. So from the definition of invertible matrix, we say that A is invertible matrix and B is its inverse. Sometimes you will be asked to find the inverse matrix which is given. So that you will study in next chapter. Some exercise problems are here. You have to work out. Find the matrix X so that X into 2 by 3 matrix, that is equal to a 2 by 3 matrix. Okay. So here, to find the matrix X, we need to know what is the order of this matrix. See here, we don't know what is the order of this matrix. So dash into dash. Okay. Dash by dash into, this order is 2 by 3, that is equal to here 2 by 3 matrix, right? Okay. And we know that in here two matrices can be multiplied if the number of columns of first matrix should be equal to number of rows of second matrix, right? So here number of columns is 2. Okay. And what about this one? Here we know that if A is a matrix of order m by n and B is a matrix of order n by p, then AB is of order m by p, first into last, right? M by p matrix, right? So here first and last, right? First and last. Okay, so the first will be 2. Okay, therefore X is a 2 by 2 matrix. Now you can find it. Take the general matrix of 2 by 2, order 2 by 2, then find it. Multiply, then you will get matrix X. Find the values of X, Y, Z if the matrix A is equal to, satisfy the equation A transpose A is equal to I. That is very simple. So find A transpose and multiply with A, then equate to an identity matrix. You will get some equations, solve the equations, find X, Y, Z. If the matrix A is both symmetric and skew symmetric, then A is, no doubt, it is a null matrix or zero matrix. It is a zero matrix. Okay. If a matrix is both symmetric and skew symmetric, then this matrix is zero matrix. Okay. Okay, they express the matrix as the sum of a symmetric and a skew symmetric matrix. We have done 2-3 problems, right, in the similar problems. Okay, fifth one, if f of x is equal to cos x minus sin x 0, sin x cos x 0, 0, 0, 1, show that f of x, f of y is equal to f of x plus y. So first you will find f of y, then find f of x plus y. Okay, after that multiply this f of x into f of xy, you will get the same thing, f of x plus y.